Well, it's official, folks. Looks like we can start. Week 10 is almost over, so we're just about getting through the whole semester. And if we're looking forward to the future, here's what we've got going on with the next coming weeks. So it looks like 2 ordinary weeks are coming up. Towards the end of this week right here, we're going to be getting information set up for our 3rd exam, really just repeating the same exact pattern you've seen on the Moodle website. So we'll have an exam week right here, then kind of a ordinary week right after. Then this will be exciting. We'll take an entire week off, kind of catch our breath. This will be a good opportunity to get caught up on any kind of work, whether it's in WebAssign or quizzes. This is going to be mostly an ordinary week, except we're definitely going to be reviewing for the final exam on Wednesday. And on this week, we don't even meet at all. I'll still be available for email questions and that kind of stuff, but this week is all about just scheduling the final exam and completing the course. So that's kind of fantastic in a way. Congratulations, folks. There's not a whole lot left to go. In fact, once we finish off section, let me get this in the right spot first. There we go. Once we finish off section 3.7, we're done with chapter 3. We're going to move into chapter 4 to look at a couple applications of the derivative, and then we'll be moving into integration. So that's what we're going, where we're at and where we're going so far. Any questions at the moment, folks, before we get started? Okay, well, we're nearly done with the section 3.6 notes, so let's finish off that last problem. Then we'll work into dealing with how to differentiate a logarithmic function. That'll be our last set of differentiation rules. So clearing this all off. Oh, I should mention, we don't have any quiz that's due this week, since last week was an exam week. There's just too many things going on to assign a quiz with all that. But we do have a brand new quiz posted, quiz number 6. And this one is heavily based off what's going on in section 3.6. So now, getting started. Here's where we left off. Well, let's scroll down to this one is the one we left off on. Before we get started, let's just collect a couple of formulas as kind of a warm-up. The major formulas that controls all of our work here is this formula. dy dt equals k times y. So this is the differential equation. It says the rate of growth or the rate of decay of y is proportional to the size of y at time t. If you solve this differential equation, we get this result. Y at time t is equal to the initial value, y at time 0, I think we color code that blue, times e to the power kt. So we have this value. This is the initial value. It could be an initial population size or an initial amount of mass. And k is the relative. Well, there's 2 things we could say, growth rate or decay rate. So let's say them both. It's the relative growth rate if k is a positive quantity. And we say instead, decay rate if k is a negative quantity. So these are the major formulas we have so far. But one big formula goes this way. If you're dealing with k less than 0, then we have a formula that says the half-life is lambda, which equals negative natural log 2 divided by k. And we can turn that formula around and just have k in this position by the red dot and lambda in the denominator. So let's say that as well. Or k equals negative natural log 2 divided by lambda. Whichever formula we use is just dependent on what the problem is asking for. So take a look at, say, part A of example 4. It's asking what is the half-life of tritium-3. That means we would use this one right here because it gives us the half-life. Let's maybe say that as well. Lambda equals half-life. So that's our major rundown of the notes, getting started on this one. Any questions or comments at all, folks, with what we wrote up here? Okay, well, example 4 is really kind of brief and terse. I think this one is kind of a confusing one. Major reason I brought this particular example to class is because there's one just like it in the homework set. I feel like doing that example there could resolve a lot of different questions. But if you get stuck on it, don't hesitate to write. I'll be happy to help out. So they tell us a sample of tritium 3. That's already vague. They didn't say how much of the sample at all, but we just have a sample of it. And all we know about it is it's decayed to 94.5% of its original amount after 1 year went by. So extremely brief question. But when they said after 1 year, that is giving us information. Decaying to 25% of its original amount is also helpful. Let's start off by just writing down some equations. This is a mass problem where mass is decaying. So instead of saying y, which you are welcome to do so, I think it's a little bit more clear to write out m for mass. So mass at time t is going to be the initial mass, m of 0, times e to the power kt, where k is the relative decay rate. So that's our equation right there. And when it says a sample of tritium 3, they're referring to this, the initial mass. We just don't know what it is. But it did decay to 94.5% of its original amount after a year. Taking that whole statement, we can write an equation that goes like this. Mass after 1 year, so mass at 1, is equal to, it says 94.5% of its original amount. And when it says original amount, they're talking about m at 0 right here. So take this, convert it to a decimal number, 0.945. Writing down these kind of word problems, oftentimes if you assume of means to multiply, you're on the right track. So what you're multiplying is the original amount. So this quantity here is m at 0. This is the most confusing part of the whole problem. Once we move beyond this point, the rest of it is just kind of business as normal with the other examples. So we should pause right here. Any questions at all, folks, getting to that stage? Okay, well, with what we're about to do on the next steps, get a little bit of space first, is start off on the left-hand side. If it says mass at 1, that means mass after 1 year, and the 1 year goes into the position of time. So on this entire left-hand side, we get to read out this equation to the left, but we're just plugging 1 right where t is. So it becomes m at 0, e to the power of k times 1. We should highlight that as well, just to show where all those things are connecting together, is equal to 0.945 times the initial mass, m at 0. So looking at this equation really carefully, one thing that happens, which is kind of an interesting miracle here, is you can just divide both sides by mass at 0. We're assuming that mass at 0 is not 0, that we really had a sample that had some amount of grams. It wasn't a 0 amount of grams, which allows us to divide here at this step since we're not dividing by 0 any longer. So on the left-hand side, all we've got is e to the power k. On the right-hand side, we have a 0.945. And whenever we got into this situation on the prior problems, all we do to solve for k or t, depending on the problem, is just take the natural log of both sides. So let me write that step in after I fix that. Take the natural log of the left. It'll be equal to the natural log of the right-hand side, 0.945. Here's our cancellation with the two inverse functions. It frees up k, and now the equation is solved for k, and that's nice. We can update our model up here. But what's not so nice is it hasn't answered the question. We wanted the half-life, not the relative decay rate. But to get the half-life, we're plugging k right here, so we did need k. This is just the intermediate step. So K is now the natural log of 0.945. Let's scroll down a little bit more. Any questions at all getting our K value? Okay, so just in case we need it on the next steps, let's also write down our updated model M of T with the information that we have. M of T is now, we still don't know the initial mass, and it looks like we never will in this problem. It's just going to be M at 0. That's the initial mass. That's the best thing we can say about it. It's e to the power of K. I probably should have kept that all in green just to show the substitution. So it's going to be T times natural log 0.945. So that's our model. And now to get the half-life, this portion right here, we use this equation up at the top by the red dot. So last step, half-life equals lambda. You don't have to start by saying half-life, but this is more for the notes, so we know what we meant when we wrote lambda. Maybe good to write down 1 or 2 times just to be sure what that represents. It's going to be equal to negative natural log 2 divided by K. So now we make another substitution. This is negative natural log 2 divided by the natural log of 0.945. Let me throw parentheses around that just to make the work similar looking. All we now need to do is just shove that into a calculator. Because it's a half-life, this has to be a positive quantity. In fact, let's say that up here by the red dot. Lambda is the half-life. It's always positive. So if you've got something that's 0 or negative, then that would indicate some mistake in our work. This is the point at which we have to grab a calculator to get going. And when you go to practice these in the homework or in a quiz problem, practice it with the knowledge that you're probably going to do the same exact kind of steps on a real exam setting for exam 3 and the final exam. So take the practice with the calculator that you're actually going to use, and it'll help out a ton. So from right here, we'll type in negative natural log 2 divided by natural log 0.945. So I got, let's see, rounding to forget 2 decimal places on this one. The half-life of tritium-3 is 12.25 years. Anyone getting any values that are different? Okay. At any point when you're practicing along with the rest of the class, putting these into the calculator, if you do get different numbers, sometimes it's a weird parenthesis in a wrong spot, or sometimes even something more subtle. Don't hesitate to ask at any point. I'm happy to do this in a different way, load up a calculator just to help out. But we've got it, folks. It's 12.25 years for the half-life of tritium-3. Now, one thing you could do that's kind of fun on this is you could be curious and just go pick your favorite browser, say half-life of tritium-3. This is not the way to answer the question, but it's a cool way to see how close were we when we used our methods. Google says it's about 12.3 years. And you know what? If we round, that's what we get, 12.3 years. So that gives us really good information that we're on the right ball track, or we're on the right track with this type of method. But any last questions, folks, on part A? Okay, we have a follow-up question. This one's going to be our last question on these notes. We're being asked, how long would it take to decay to 20% of its original amount? So we know it took 1 year for about 5.5% of it to disintegrate. So now we're updating to this question. For where the red dot is, the question is mass of T equals 0.20 when it says of its original amount. It's referring to mass at time 0, its initial amount. So that's how our equation starts. That's why we updated the model right here. We are going to need it at some point in all these kind of problems. So we're going to take this, I'll just highlight this temporarily, and plug that right here where M of T is. So we've got initial mass. e to the power of t natural log 0.945 equals 0.20 times the initial mass. So that's our really big substitution on this one. All we've done is on the left-hand side where m of t is, we just threw in the function that we built right up here. Now, next step, the one you're probably anticipating already, is we have the same quantity on both sides. It's not zero. The problem doesn't make sense if it's zero, so we can divide it out. It's just gone from the problem. After doing that, we want to take the natural log of both sides. So we're on this step right here, essentially. We're just solving for a different quantity. We're solving for time this time. So natural log e to the power t times natural log 0.945 is now the natural log of 0.20. That gives us a cancellation. And on the left-hand side, it's just t times the natural log 0.945, now set equal to the natural log of 0.20. So final step, folks, t is going to be the time for it to disintegrate to 20% of its original amount. And by the models we built, it's exactly this figure. Natural log 0.20 divided by natural log 0.945. But you can expect for a question like this one, we need to actually get a value out and approximate it. So we'll round this one to 1 decimal place. Any questions whatsoever, folks, on this approach? Okay, so last calculator job. This one is going to be natural log 0.20. I don't know why, but I feel like I need that zero there to make sure that I really put it in accurately, but it doesn't matter. Natural log 0.945, and looks like if the half-life we said was about 12.3 years approximately, then to get down to 20% of the original amount, we need to have about 28.5 years go by. You know, that sounds about right. It's in the right ballpark. If this said 2,800 years, that sounds way off. And if it said less than 12.25 years, that would also be way, way off. So the value we pick, let me close that so I don't keep on grabbing it, is going to be 12.5 years. Excuse me, 28.5 years. I feel like I need to double check that value real quick here. Okay, I think we've got it. Well, any questions, folks, on the solutions for this part, last example? Okay, well, congratulations. This was our bigger applied section in chapter 3, but honestly, it's kind of just a rehash of what you would have done in pre-calculus, dealing with these exponential models. And the major thing to watch out for this kind of problem is anything that goes along these lines. If they ever ask for at what rate is something growing or decaying, that means you're using the part of the formula where you just take k times an amount. So in other words, this formula does get used a lot in actuality, the one at the very, very top. But let's now move into derivatives of logarithmic functions. I have this document right down here that came from the very, very top of Moodle. We're going to be using that quite a lot on these notes, kind of just side-by-side mode. This is a big document, but the major takeaway is not so much the initial stuff. This is good reading if you just want an introduction to logarithms, domains and ranges, those kinds of things, what their vertical asymptotes would be. Then when you scroll down further and further, we have some examples. But right where it's yellow, I think this is going to be the major part for the class right here. So this is where the properties we're going to be using to make differentiation just a little bit more streamlined in this section. And like we mentioned, logarithms are pretty tricky in this class because they're tricky on their own. And so to really get great at this section, it's important to really know what's going on with logarithms. If you feel like you're pretty rusty on it, go to the very top of the Moodle website and look at this logarithms worksheet. This is a great crash course for everything you need to know for logarithms in our class. Well, any other questions, folks, about the review materials before we jump in to 3.7? Okay, well, let's give this all a try. In 3.7, we start off with just a couple new differentiation formulas. They always look a little bit mysterious until we just become more and more familiar with them. And so here's our next set of formulas. In fact, looking at these, I want to format this slightly differently. Let me move these to the left. Sorry, if you printed this out, that's a little bit harder to do. But what I want to do is kind of think of this as a big grid. Because some of the stuff that we've done is similar to what we're dealing with right here. So in particular, if your base is E, we have some pretty fast derivatives. On the right, if you have, say, y equals e to the power of x, then its derivative, dy dx, is just itself e to the x. So this is a great format whenever we're dealing with the base e exponential, where the base e is about 2.71. Always good to write that down or think it to remind us e is nothing mysterious, just a rational number like pi. On the left, it's kind of a nice formula. It says if you differentiate the natural logarithm of x, all it does is place your x in the denominator. That's not something that's easy to prove. You have to use a chain rule in a really, really clever way. But what's great about it is this is a fast formula to actually practice. So, for example, if y is 5 natural log x, then the derivative of y would be 5 stays where it is, because it's a constant multiplying the natural log, derivative of natural log x. By that formula, it's just saying x goes down below into the denominator. And often we just do it that way. It just goes right under the constant 5. Any questions, folks, with these two examples on the left and the right? Okay, so think of the bottom left, the bottom right panes as being kind of the special cases, the ideal cases where differentiation is just a little bit easier. But if you don't have a base e and you're dealing with something like this, a random base that has to be a positive quantity, it can't equal 1, then your derivatives get a little bit tougher. So here's the derivative of natural log base b of x. It goes 1 over x natural log b. That's kind of strange, but there is a great way to think about this. Don't think about this formula as being totally in isolation. Just like that formula, oh, that doesn't work. Let me try again. Just like this formula and this formula, they actually go together. You want to think about them at the same time. So the one that goes with the formula up above is this function. If y is just b to the x, then y prime would be b to the x times the natural log of base b. For just a really quick example, if y is, say, 3 to the power x, then the derivative y prime is 3 to the power of x times the natural log of 3. There's no natural log of base e over here anywhere, but that's because of properties of logarithms. Properties of logarithms tells us the natural log of the base e is 1. So we didn't need to put natural log e here at L. It would just be times 1 if we did. So these are pretty tricky formulas. If you're like me, you might have forgotten how they go because they don't come up a ton. But when they do come up, if you suddenly have to differentiate this, that's pretty confusing unless we refresh what the actual formula is. The thought is, it goes just like differentiating the exponential, except we multiply by the natural logarithm of whatever the base is. Same over here then. There would have been natural log e down the denominator, but that equals 1. And this is the generic case. If it's an arbitrary logarithm, you go 1 over x times the natural log b, which mirrors this portion. If you're differentiating an exponential function, you get the exponential multiplied by natural log b. So really the big difference here on this logarithm formula, oh dear, that's hard to erase. Let me put that back. The big difference on the logarithm formula is just that the natural log is multiplying x in a denominator. So for a really fast example, if y equals, say, log base 8 of x, then its derivative, y prime, is 1 over x, natural log 8. So those are our brand new formulas. The new ones are the two on the left, but we did a whole bunch of other stuff on the right just because they are still very relevant. And once again, think of this formula and this formula as being really two sides of the same coin. Any questions at all, folks, with those formulas? I can even zoom in just a touch there. Okay. Well, now that we have all those formulas on the table, here's a couple quick derivatives we can calculate right away. On the left, I have the cube root of the natural log of x. And on the right, we have natural log of the cube root of x. And to your eyes, those might look kind of the same, but they're really totally different, and so are their derivatives. So I'd say the bigger takeaway with this problem here is telling the difference between either one. Let me scroll to this point because we need this formula right here. First thing we want to do is just rewrite these functions in a way that makes it easier to differentiate. So I'll think of f of x as blue, g of x as green. Step one for f of x is not to differentiate it. That's kind of confusing to differentiate when there's a radical expression. Instead, we need to write it as natural log x power 1/3. And it makes it totally easier to differentiate in that format. But what about g of x? G of x is a little bit different because the cube root is inside the natural log function. So let's rewrite g of x as natural log. It would be x to power 1/3. So that's our step so far. Well, it turns out the one that's easiest to differentiate is the function g. And not because of the format it's in currently. G is only easier to differentiate because of properties of logarithms. So if we pull up those properties, the big property we're going to use is, let's take a look, property number 7. Property 7 says, if you have a power in this position, raised, say, x raised to a power p, it can become just a coefficient. So the power can move down in front. So over here, a power of 1/3, we're going to pull it out in front in that way and make it a coefficient. Let's state it right here as well so we just know that formula. Log to any base, I'll call it log base b, of a to a power, is the power times log base b of a. So applying that, down below here, g of x turns into 1/3 natural log of just x. Suddenly, this one is a far, far easier derivative. It's just a constant, 1/3, multiplying by the natural log of x. We already know the derivative of natural log x, just turns into a 1 over x. So let's differentiate this right away. G prime of x now is going to be 1 over 3. Differentiate x, puts it in the denominator, and so it just joins x in that way. It's now 1 over 3x. Well, any questions, folks, with dealing with function g? Okay, one big takeaway with what we did in function g is we simplified it actually quite a lot. Right here, where the red dot is, that is a chain rule problem, absolutely. The inner function is x to the power 1/3. The outer function is the natural log x. So taking this one step, this eliminated the need for the chain rule. And that's a super important observation. In this section, some of these derivatives might feel like they're actually really, really hard, that you need some extra help, that the homework assignment is totally unfair. That's not actually the case. The derivatives are easy as long as we're using properties of logarithms and thinking about them all of the time. We have to simplify a bit before we get started. However, you can't always use properties of logarithms In this format right here, there is no helpful property for us. This one is a chain rule for the function f of x in blue, no matter what we do with it. So let's start analyzing it as a chain rule function. The outer function is this one. The inner function is natural log x. So the pattern for differentiation, we'll go differentiate that first. Oh, sorry, I missed the chat. Jamie says, will you give us these 7 rules or should we memorize before the exam? You know what? I hadn't actually thought about that. Thanks for mentioning, Jamie. This is a lot to memorize, I'd say, for the purpose of the exam. The idea with this class is you just need to be familiar with them. But I think most people are focusing on memorizing the calculus. So I'm going to make a quick note here that I'm going to come back to. I think it is fair to put this on the real exam because it's so pivotal to this one section. So let me make a note. Include properties of logs on last page. Okay, I ran out of post-it notes, but I'll put this in my documents right away and make sure that happens when we go to write exam 3. Thanks for mentioning that, Jamie. I think that just makes sense for this section in the first place. Other questions at the moment? Okay, well, let's give this chain rule process a try here. It's actually not too bad. We'll go f of x equals. I always go 1 and 2 just as a reminder for me, the order to do this. So we differentiate the outer function first. 1/3 comes down. The power is 1 less. So subtract 3 over 3 to get negative 2/3. We multiply by the derivative of something, and let me put down a border. There we go. The thing that goes inside both of these placeholders is now the inner function, function 2. So natural log of x here and here. When we go to take care of this derivative of natural log x, all we're doing is that right there. That's just going to place an x in the denominator. So the last steps are, this is 1/3 natural log x to the power negative 2/3 times 1 over x. If you left your answer in that format, I'd say that's completely fine. That's a kind of a stylistic choice to do anything further to it. I usually leave my exponents in the numerator, even if they're negative, unless I know I'm doing something further with the function. So the one step I probably would take, which isn't anything major, is write it this way. Natural log x, power negative 2/3, just going to leave that as a negative exponent. And 3 times x, I just took the denominators, multiplied them together, and threw them down there. Kind of similar to what we did with the function g. When we differentiate natural log x, that is a 1 over x here, but a fraction times a fraction is just going to combine the denominators. So the thought is really x just goes to that denominator. Well, these are 2 tricky functions, but the reason for doing them both at once is it's good to tell apart why we had to work so hard on the function in blue versus why the function in green was easier. If logarithms apply, then the derivative is always reduced and sometimes by a lot. Any questions further, folks, on example 1? Okay, well, let's keep on going through the notes. With what I have going on the next set of notes are a slew of problems which are pretty similar to what you're going to see in WebAssign. It says for the hint, use properties of logarithms where possible. So it's not always possible to apply them. For example, nothing helps us out with part A right here, but something definitely helps us out with part B. So we'll try out some properties of logarithms and derivatives in example 2. Example 3 is like our hard one, where this is a problem that if you were to do this without using properties of logarithms, it is just a total nightmare. No one wants to do, let's see, a chain rule involved with a product rule, involved with another chain rule, and so on and so forth. This could take a half an hour to do, and no guarantee I'm going to be accurate. But if you expand it and then differentiate the result with properties of logarithms, this one's not so bad. Then I have a random formula at the end of the notes that does come back in chapters 4 and 5, and we'll practice a little bit with this one. So these notes are kind of short. This is just the last bit of chapter 3 that we're taking a look at. Well, let's start calculating our derivatives, Any questions or comments so far before we run through the rest of these? Okay, well, it looks like we have another chain rule on part A. I mentioned properties of logarithms don't work on that one. But it's good to look at the set and really think about why. There's minuses and pluses, and if we look at here, properties 5 and 6 have minuses and pluses, but that's between the different logarithms. The properties we want to try to apply when they work are for minuses or pluses or multiplications and divisions on the inside of the function. Notice there's a multiplication formula, a division formula, an exponent formula, but nothing else. Just like in algebra where square root of a plus b is not equal to the square root of a plus the square root of b, same problem with logarithms. Natural log of a plus b is not equal to the natural log of a plus the natural log of b. And the more you look at these properties, the more you start to realize, for some really weird reason, pluses and minuses in algebra mess everything up. But if it's multiplications and divisions, suddenly you have stuff you can work with. Lots of formulas for those. So no properties at all can be applied to this one. So we're just going to analyze it as a chain rule. The inner function is the thing that goes inside the natural logarithm. So this all right here is function 2 inner. The outer function is just the natural logarithm. So this one right here is function 1 outer. That means when we go to differentiate this, let's maybe color code it as well. The first derivative we're taking is for the natural log of x. We haven't done it a lot, so it's also stated here. Natural log x prime, so now we're differentiating it, is 1 over x. So in our problem, when we apply that property, we can say y prime equals 1 over, here's where x would go, but we have more than just x, there's a lot of stuff. Let me make that actually a little bit bigger. 1 over 1 big placeholder. So this big placeholder you see here, that's in place of where x was. Then because it's a chain rule, we're going to multiply by the derivative of something else. So that's our setup essentially every single time with the chain rule. Next step, go to your inner function and plug it into both of the placeholders. So 9x power 7 minus x power 6 plus 5x minus 11, and then write it again, 9x power 7 minus x power 6 plus 5x minus 11. In the denominator, the parentheses can now just be totally dropped. I only put those parentheses in just to indicate that was a placeholder. But for this value right here, we're going to differentiate it. Because it's multiplying a fraction, we're just going to multiply the result right into the numerator. So here's how this problem ends up. 9x power 7 minus x power 6 plus 5x minus 11. Black to just say we copied and no change. But differentiating this thing is going to give us term by term 63. X power 6 minus 6. X power 5 plus 5. Derivative of the constant would go to 0, and so that's the whole result. Well, we did it, folks. This looks like it'd be a really nasty one, but actually these are not too bad. The whole thing that happened was the derivative of natural log x places x into the denominator. So we did that right here. We took all of that and we threw it down below. But the chain rule says you have to multiply by that derivative. So we differentiated that. It went out into the numerator. Those are some crazy arrows, but let's take a look at it again. So in the punchline to all of this is your input goes down below. Then the derivative of your input goes into the numerator. So if you like that shortcut, I think it's a pretty decent one for this process. I'll always show this step in the middle on these notes because we're still just learning it. It's good to see how it goes together in stages. Any last questions at all, folks, with part A before we try another? Okay, well, part A, no properties of logarithms work, but we can use those properties on this one. We must use properties of, I'll just say logs for logarithms. That's just too big of a word to write out every time. I use a strong word, must. It's not as if you'll get the wrong answer if you didn't use properties of logarithms, but the word must is just to say this is the best way to calculate it. It's highly encouraged, and it'll get you in a great shape for moving through these problems quickly in an exam setting, so you're not getting bogged down with tons and tons of unnecessary steps. So if properties of logarithms works on these, imagine you're doing this as a real exam, like we were mentioning earlier. I'm going to put this on the real exam. So anyone see which property actually applies 1 through 7? Feel free to just say it out or call it out in the chat. Which properties of logarithms can we actually use on part B?
Is it that number 7?
Let's see. You know what? Yeah, we could use number 7 on this one. Good call. I was thinking property number, let's see, where was I at? I was thinking property number 1, but doing it with number 7 can make it pretty clear. So property number 7 is going to allow us to take the x and make it a coefficient. So now f of x equals x natural log e. And I'll say that this is property 7, just as a paper trail. By property, we're referring to these ones here. So now that we've done that, there's one more properties of logarithms we can use on natural log e. Any volunteers to say which property of logarithms that would be, or just what would happen to natural log e? It seems like it's definitely kind of confusing in a way. So if you're not sure, don't worry, I don't think you're alone. Let me fix one small thing. That looks like lim, not natural log. But one thing that's tricky about the properties of logarithms is when you look at them, they all say log base b, every single one of them, yet we have the natural log. L is logarithm, N is natural, so this came from French. They say logarithm naturel, so it's Ln. So if we're dealing with a natural logarithm and we want to use the properties of logarithms, we should think about what is the actual base to that thing. Let's write this out in the scratch margin. Natural log of x really just means log base e of x. So if that's the case, natural log of e really means log base e of e. So it's really hard to find the right properties of logarithms if you're looking at that. But if you're looking at this portion down here by the red dot, it more directly lines up with one of these properties. Any volunteers to say which property we can use for log base e of e? I could tell this is kind of a confusing subject. This is one of the reasons why I usually actually go kind of slow in this section. Section 3.7 is, sure, differentiating logarithmic functions, but we're really doing two things at once. We're also refreshing what logarithms are and how to even use their properties. So the trick for this one right here, log base e of e, is it's property number 3. If you have log to a certain base, but you input a value that equals a base, we always get 1. And the reason for that is the output to the logarithm 1 right here is the exponent. you have to put on the base in order to get the input. Since b to the power 1 equals b, this right here just outputs a 1. Similarly, down over here, log base e of e, this turns into just as a 1, just as well. But another thing to think about is we've actually been using these kinds of properties a lot. Let me show you what I mean. Let's pull up again section 3.6 and give it a minute. It always takes it a second to load up a second Word document. These things get tired after a while once they get filled out, I think. And let's see. Oh, right there even. On part A of example 2, we had e to the power 3k, but then we took the natural logarithm of e to the power 3k. Notice we did this weird cancellation this way and got just a 3k out. The reason that worked was it was property, let's see here, where am I looking for? Property number 1. Instead of log base b, you could put ln right here. ln of e to the x is just going to cancel all of that and just leave 3k. So we're using property 1 a lot just to do a cancellation this way and get an x out. Likewise, on this problem, if it's natural log e, we could have just canceled that all together and get just x. So f of x is actually just x itself. So doing it in stages, you could write x down as an exponent using property 7. Then if you did that, natural log e is 1, and that is through, I forgot the property number 3. All right, prop, just a shorthand for property. And then finally doing all that, again, there's a couple ways to do this. If you decide to go that way, just cancel, then I'd say that's a fine approach. It's not at all different than we did when we did this. Just cancel natural log and the base c exponential and keep the exponent. So if you did that, you'd skip down to the very last step. But doing it in stages this way, that's also good because we're practicing properties of logarithms even more that way. But no matter how we do this, if we take the long way with the chain rule, or if we simplify, the derivative is done. F prime of x is just the derivative of x after all, and the answer is 1 to that problem. Kind of satisfying in a way, and if you like, you could try it with the chain rule, you get the same exact result. Any questions at all, folks, with our part B? Okay, so far, part A, we just differentiated directly, no properties applied. And part B, we're doing some kind of cancellation, either right here at this step or at this step, and we were just differentiating x. Now, when we get to something like this one, I think that needs a little bit more space. There's a lot more things going on all of a sudden. Move that just to the next page, that should work out. Trouble with this function is, well, we can use properties of logarithms right here where we have a cube root, and we will for sure. But we also have some multiplication going on. That means this problem at its heart is a product rule problem. Before we even analyze the product rule, we want to take advantage of properties of logarithms as much as feasibly possible. So let's start off by just writing out h of x again, but I'm going to change the exponent, or excuse me, change the cube root into an exponent. So h of x is 15x log base 7 of 2x, that was almost a 3, let me fix that, log base 7 of 2x minus 8 to the power of 1/3. So that's our standard trick. Notice we've used that trick pretty much this entire class of taking a radical, changing it into this format. Once we get here, we want to use property 7. Let's visualize it before we use it. We're still learning this, well, relearning this kind of stuff, refreshing it. Property 7 says you can take an exponent p and make it a coefficient. That's what we're going to do with this 1/3 right there. It's going to move out in front. Multiplication's commutative, so we'll just put it in front of the 15, say. If you divide by 3 and just wrote in a 5 on your next step, that'd be just fine as well. So this one is property 7. Actually, let me write it down this way. where the result is of using property 7. We have 15x. The 1/3 that's there comes down as 1/3 log base 7 of 2x minus 8. So let's do a division next. And now we have definitely a simplified function, maybe not by a lot this time, but you know what? Any bit helps a lot. The problem is complicated already enough. So we get 5x log base 7, 2x minus 8. Here's where we're going to begin the product rule. There's two factors, 5x, that's going to be our first portion. And the second factor is log base 7 of 2x minus 8. We need the derivative of an arbitrary base logarithm, not the natural log. So it's stated down here. Log base 7 of x is 1 over x times natural logarithm of 7. So now we're about ready to start the product rule process. Any questions so far to this stage? Oops, didn't mean to draw on there. Let me fix that. Okay, let's write this out. So if you're a fan of Leibniz notation, I've been neglecting it a lot this class. The derivative h prime of x can also be written dh dx. So we've got a derivative going. Organizing, we need 4 placeholders if we're using the product rule. So let's go. So 2 things multiplying. Don't forget the prime symbol to indicate you're differentiating as well. On the second set, alternate where the prime goes, so it's on the second factor. Then take your first factor, drop it into the first positions. Kind of made those big, but oh well, at least it fits. That's what's important. Now take your second factor and put it into the remaining positions. Log base 7, 2x minus 8. Log base 7, 2x minus 8. So that's our format. First derivative is no big deal. That's just going to turn into a 5. Then we copy through all the way to this point. But this derivative is definitely new. Sure, derivative of log base 7 of x looks like that, but this one's also a chain rule, so let's be extra careful. In the chain rule, the thing in the inside is the inner function, 2. The entire log base 7 function is the outer function, 1. 1 to say we'll handle that differentiation first. So this is the whole write out of the product rule. We're going to do a chain rule right here. Might as well say that. And then our problem is going to be complete. Any questions at all, folks, with the analysis here? Just getting into the right format? Okay, let's differentiate this thing. Derivative of 5x, that's just a 5. I'll use blue to say we changed something, differentiated, and I'll go to black just to indicate we're copying now. So 5 times log base 7 of 2x minus 8 plus 5x. Now back to blue, where we differentiate to this function. It's a tricky derivative because it's in this process, but where x is, we're going to put in just a big placeholder because we have a chain rule going on at the same time. So derivative of the outer function is going to be times 1 over something, there's our placeholder, then multiply by the derivative of whatever that something was. The something we keep referring to that goes in the placeholders is the inner function, 2x minus 8. Copies in this location, no change. Copies in this location where we do one final derivative. So almost there. And again, if we never use property 7, this derivative would have been really, really awful. It would have been a chain rule with 3 functions at once, just way too much going on. So anything you can use to simplify the properties of logarithms is a big help. This is a long question already on its own. So let's finalize this out. We have 5 log base 7, 2x minus 8, plus, so 2x minus 8 in this denominator. When we go to differentiate here, we get a 2 and nothing else. 2 is going to multiply in the numerator, but so is 5x. So altogether, 5x and the 2 multiply to give us 10x. Well, there's nothing further to really do on this thing. You know, I guess we can do one little thing. You could reduce this by dividing numerator and denominator by 2. I don't think WebAssign is too picky about reductions. Correct me if I'm wrong on that. But just in case they are, that's a good step to take next. Oh, great question about that, Jamie. That was a mistake on my part. It absolutely should involve the natural log of 7, and this would have been a terrible way to lose points on this question. Thanks for spotting that. Natural log 7 should have been right here, and then it should have been included right here. That's a bad one to have forgotten. If this was a real exam question, out of 5 points, I feel like that's enough to take off 2 points because that is a huge feature of this derivative. Thanks again for spotting that, Jamie. Any other questions, folks, to this stage with the correction? Okay, with that critical correction put in, let's do the less critical, just reduce the fraction. I'm going to divide numerator, denominator by 2, and we get 5 log base 7, 2x minus 8, plus, oh, forgot to reduce. Try not to use Control Z because I noticed it deletes things totally randomly on my page. That's really weird. But we get 5x divided by x minus 4 times the natural log of 7. I feel like I should highlight that. That's an easy one to miss. Well, any questions at all, folks, with that kind of a nasty derivative on this one? Okay, well, we don't have too much left over on these notes, but the next one is going to be the big properties of logarithms kind of problem. This one could make it to exam 3 or potentially the final exam, and it would be formatted in this kind of way as a real exam question. There's more points in doing this part because that's the whole fundamental portion of how we're going to differentiate in part B. So part A is worth even more points than would be typical. We want to expand this function as much as feasibly possible using properties of logarithms. And some people are really good at this. Some people do it in just one step. If you're that kind of person, I think that's awesome. You obviously use logarithms a lot, and that's really great. But I think for most of us, it's easy to get rusty on logarithms because we don't use it every single day of our life. So I want to do this one in stages, one property at a time, just to show methodically how this all goes. So the very first thing we want to take care of is the fact that there is division in this problem. When we cite properties of logarithms, it's property number 6 that takes care of that. A division inside your logarithm function turns into a subtraction of those logarithms, where you have the numerator here minus the log of the denominator here. So let's use that right now, property 6. Property 6 will take t of x and write it now as log base 5 of x cubed times, this is a 5th root, and if we're looking ahead, we know that's not really helpful for us. Let's write it as a power 1/5. 7x minus 8, power 1/5. And then this is what made property 6 come into play. The division turns into a subtraction of log base 5, x power 5 plus 3 to the 4th power. So that's our first step with property 6. Now, there's a bunch of other properties we could use again and get to the total answer. But I'd say the next thing you'd want to look into is breaking up this, where the multiplication is. It's kind of the reverse of property 6, because property 6 says if you divide, you're using minus. But property 5 says if you're multiplying your inputs, then you go to a plus, log of the first input plus the log of the second input. So that plus right there, that multiplication right there goes to plus. And in a certain sense, that's not too unexpected because the product rule involves a plus in the numerator and the quotient rule involves a minus in the denominator. That's kind of a cool pattern to think about to just tie together those formulas. So this next one is going to be property 5. property 5, we're going to go log base 5 of x cubed. This multiplication here turns into a plus. Actually, don't want to highlight it there. Let me fix that. That multiplication there turns into a plus. Just go that way. I think that's more helpful. Log base 5. 7x minus 8 power 1/5 minus log base 5 x power 5 plus 3. Forgot that was a bracket to power 4. So methodically, stage by stage, here's where we're at so far. Does that look right to everyone at the moment? Okay, last property to deal with is all those exponents. They're kind of inconvenient. These are all chain rules if we don't move them. And some of the chain rules are worse than others. This one has an outer function, a middle function, power 1/5, and an innermost function, 7x minus 8. This one's just a pain to do as a chain rule. But if we use property 7 a whole bunch of times, the complexity gets reduced massively. Property 7 says an exponent on your base becomes a coefficient. So property number 7 is going to work with power 3, power 1/5, and power 4. So here's our last step. This turns into 3 natural log, log, not the natural logarithm. 3 log base 5 of x plus, next exponent coming down is the 1/5 highlighted. 1/5 log base 5 of 7x minus 8. Then last one. We had minus to start, but an exponent of positive 4, highlighted in yellow, now comes down, multiplying log base 5 of x power 5 plus 3. So finally, we're about ready to differentiate. We have not so bad derivatives any longer. And again, if you want to just compare, if you ever get bored and maybe having trouble sleeping, anything like that, try to differentiate that function outright without using any properties of logarithms. It's kind of an interesting adventure, and you can see why I would never want you to actually do that in an exam setting. It's way too messy and complicated. But this as a derivative is totally feasible as a real exam question. Any questions first at all, folks, before we go to differentiate it? Okay, let's set expand fully, which is what we did here. We didn't do anything with 7x minus 8 because there's no properties for that, nor for x power 5 plus 3. First derivative here is going to be straightforward. This one's a chain rule, so let's be a little bit careful. We have two functions. 7x minus 8 is inner. Log base 5 is function 1, outer. And then we'll do it again. Same kind of analysis. Log base 5, that's function 1, outer. And x power 5 plus 3, that's function 2, inner. So here's our final answer. From t of x, now equal to all that, we can say t prime of x. When we go to differentiate, the 3 stays right where it is. X goes into the denominator. And don't forget about this part as I did last time, because it's log base 5, we multiply by the natural logarithm of 5. Doesn't hurt to just restate that, I think. Let's say it here. So that's our differentiation formula for a particular base 5. That takes care of the first term, so that's kind of exciting. We're on our way. Now, moving down the line. Constant multiple rule says 1/5 is not affected. We differentiate the outer function to start. That just puts stuff in the denominator, but combines it with the natural log 5. Then we multiply by the derivative of something in the numerator. I usually write it out here, but if you're getting short on space, you can also just put it right in the numerator. And that is the punchline. It's going to go in the numerator in the next step either way. So I'll visualize it this way, slightly differently. Thing going inside both of them, let's use green, just since that's been our pattern of chain rule. 7x minus 8 here and here. So this derivative needs one more step and we'll be all set. And just moving on down the line, next one goes minus 4 times, same pattern for this derivative. We take something and put it in the denominator. And we multiply by that same thing. We're multiplying it into the numerator this time. That's the inner function, x power 5 plus 3. So it goes below and above. Let me just move this so we can always see the clock. There we go. So just about done, folks. 2 more derivatives to go, maybe a little bit of a simplification, and we'll have our results. So next step, 3 over x, natural log 5, no big change there, plus, on the second fraction, I'm just going to put all the constants together. So it's going to be 5, I'll leave it in factored form. If you wrote this 35x minus 40, totally fine as well. But don't forget parentheses and then natural log 5 to make your answer totally algebraically correct. Without those parentheses there, WebAssign wouldn't accept the answer. In the numerator, we're just doing that derivative, so 7 goes up above. Then it goes minus on this one. Denominator is x power 5, plus 3, and it looks like I forgot something on that one. Geez, I don't know why that's so hard, but that should have gone into that denominator as well. So if you're getting ready to make that comment, good on you. That was my mistake again. Let me put it in here. Natural log 5 and natural log 5. Again, that's kind of a serious mistake. That's more than a 1 point lost potentially, because that is the punchline to this derivative that you have natural log 5 in there. So let me highlight those in yellow just for safety once again. So sorry for that slight distraction and correction. So where we're at, I copied in x power 5 plus 3. In the numerator, we're going to differentiate it, and we have 4. Coming from that negative 4, I just pushed it into the numerator. Derivative of x power 5 is 5 times x power 4. So it looks like one more step to take and simplify 4 by 5. If you erase your notes and put a 20 there, I totally get it. It's a lot of writing to the next step. But you know what the good news is about this whole process? You never are expected to find the least common denominator and add these together. Just leave your answer in an expanded form, and that's always totally acceptable, reasonable, and super expected in the first place. So this answer ends as 3. Divide by x natural log 5 plus 7 over 5, 7x minus 8, natural log 5, just a lot of copying. And here's my one change, 20x in the numerator, 20x power 4, then x power 5 plus 3 times natural log 5 down below. Finally, that's it, folks. That's our total derivative for this horrendous function. You know, the real hard thing would be to try to come up with a word problem that ties in with the function in that form. But aside from coming up with something like that, that's how the derivative would come down. Any questions or comments whatsoever, folks, with our end answer? Just fixing my penmanship a little bit over here. Okay, well, looks like we have one last problem for the day, and then we'll call it a day and a weekend. So here's our last one. This form is pretty interesting, and the author discusses how that it's derived in the notes in the reading. The idea is if you break up the absolute value of x into a piecewise function, this could be defined as x provided x is greater than or equal to 0, or negative x if x is less than 0. That's just one way to define the absolute value of x. Another way is absolute value of x is square root x squared. So that's another curious formula there as well. But the way you derive this one is you break out absolute value of x into cases, differentiate both cases, and you'll find with the chain rule, you get this, 1 over x. The absolute value bar is totally eliminated for this derivative. It's kind of a side niche case, it feels like, in chapter 3, because we really don't do a lot with that. But the warning about this one is, this comes back, in the last section, in chapter 4, and in chapter 5. So think of this formula here as kind of a preview. We'll come back to it and practice it again once we're using it once more. So it's a pretty fast process. Even if there's a whole bunch of stuff in this function, all that's going to happen when we differentiate is that stuff goes into the denominator and we multiply it into the numerator. But it's still a chain rule problem, so let's go carefully. In the chain rule process, the function going inside is the inner function, function 2. That means the natural log function is function 1, the outer one. So for differentiating y, let's use Leibniz notation just because this is going to be our last computation. Differentiating y would be dy dx equals something goes into the denominator. You can put that placeholder prime into the numerator if you prefer, or if you'd like to write it out slightly more expanded, it could be written this way. Either case, like we discussed before, this whole thing is going to go into the numerator either way. Lovely that we have the natural log, so no chance for me to forget like something like natural log 5, but watch out for that. That is kind of tricky and easy to miss. Next thing we do is grab this inner function, throw it down below, place it over here where we'll differentiate it. So here's our last step, or our second to the last step, x cubed plus 4x squared minus 1. This derivative, we'll calculate it and multiply it into this numerator over here. So we have 3x squared plus 8x. And well, we're done with the first half of the problem. We found dy dx. Last thing to do is evaluate it when x is 2. But any questions to this stage? Does that look all right to everyone? Okay, well, here's our end answer to this then. The derivative of y with respect to x evaluated when x is 2 just means we're throwing 2 for x's. It becomes 3 by 2 squared plus 8 by 2 divided by 2 cubed plus 4 times 2 squared minus 1. So in the numerator, it looks like we have 3 by 4, so that's a 12, plus 8 by 2 for a 16. Down below, it's an 8, plus, this is 4 times 4, so 16, minus 1. So in the numerator, we've got a 28. In the denominator, that looks like 23. That took me a moment. Let me know if my arithmetic went sideways on me, but looks like 28/23. And 23 is prime, so this fraction doesn't even reduce. I'm totally fine with the improper fraction. Well, we did it, folks. That's our last derivative and evaluation for the day. When we come back on Monday's class, we're going to be moving forward into applications of the derivative, chapter 4. Any questions at all with this last problem or any of the others? Okay, well, have a great afternoon, everyone. I'll be back on office hours if you have any further questions. Otherwise, I'll see you next Monday. We'll be already in week 11. You bet. Have a great one.